Hello, everyone. A very good morning. My name is Harish Potukuchi. So I'm responsible for simulation and material modeling at Foray Engineering. I would also like to introduce my colleague and my co-presenter today, Mr. Christoph Schober.
Hello, everyone. I'm Christoph Schober. I work at Foray Engineering in marketing and simulation. And together we planned a very fine session for you today regarding the MAT24 and a simple failure approach.
Okay, so let's begin with a small introduction. So basically, in the last couple of days, my colleague, Mr. Reithofer, on day one spoke about our different products, VALIMAT, IMPETUS, and on day two, we had my colleague, Mr. Stefan Riemelmoser, who gave a very deep insight into our IMPETUS test machine. So, material data generation for simulation, the recap from day one. What is the current situation with material data generation? So the current situation is that we have more and more data. So and we have a lot of different load cases like compression, shear, in addition to the classical load case of tension. What is also the requirement is more complex simulation models and more investigations on failure. What is then needed? And what is needed is a smart user interface, a user interface that can also handle optimization and also big data. Okay, so this is where our software solution VALIMAT comes in. The big advantage of VALIMAT is that it's an integrated software solution where we can handle big data. We have complex models that are generated automatically, and it makes it easier for a good correlation to simulation. So basically, this picture should be familiar to our listeners who are here on day one. Basically, this shows you the entire ecosystem of VALIMAT. So we have the test results, we have the test results from our impetus and also from external test equipment. And we have databases that basically store data. Also, the test data or the test equipment is coupled with camera systems. And then we have our optimization and simulation workflows. Basically, what VALIMAT does is we have automated finite element model generation. So basically on the test load cases that you have tested your material, you can easily validate them on the same load cases with the same exact setup using the automated models that are generated from VALIMAT, which include the aforementioned cases like tension bending. We have double X ribs. We have tension bending. We have puncture tests and also the classical tensile test. Okay, this picture also was shown on day one, where this is a brief overview of the graphical user interface of VALIMAT. All right, so VALIMAT is basically subdivided into 5 parts here. The GUI of VALIMAT. So number one shows you all the test data. So it's the test database. Number two shows you the window number two on the top right shows you the visualization of the test data. The bottom left shows you the model database where all your simulation models are stored, and bottom right basically is your model visualization window where you can compare your simulation models with the test data. And then we have the vertical window here, which is our basic menu. And you have different options there. You have the database tab, you have test data tab, you have the measurement tab, the evaluation, parameter models, optimization, and also in addition, post-processing module. So what we will do in the rest of the session is to get you familiarized with VALIMAT. How do we set up simulation models? How do we validate the tests that we have conducted to come to a material card? In this case, so not only LS-DYNA material models, but we support a large number of models in Abacus and PAMCrush too. And the next important feature is that if your models, if the model that you want is not supported by VALIMAT directly, there is an option to define user-defined material cards, which would be the focus of the talk from my colleague, Mr. Hirschman, next week. Okay, I will now hand over briefly to my colleague, Mr. Dober. He will take you through the next.
All right, thank you for the very fine introduction, Mr. Potoguchi. First of all, what do we need to basically get familiar with the hands-on software? What are the objectives and the requirements? The objectives we want to produce are basically using or creating, generating a MET24 on shells, based on 3-point bending measurements conducted with our Fourier impetus. Therefore, as Mr. Potoguchi already said, we do need a smart user interface and especially a possibility to handle the big data. We use databases, handle the big data, such as this one. This database is already pre-filled with test data. But as we can see, we can implement our own databases and have selected templates beforehand. For an example, I will import a database right away, just so you can see it. We have our template database. Here's, for example, 5 different velocities. We'll click open. We'll select new IDs so it doesn't overwrite our previous tests, and then we'll import the whole thing. This doesn't take much time, as you can see, and we already have all of the blankly filled test data, which are already preset to 3-point bending. The gauge length and everything is already pre-adjusted, selected. And we also have evaluation for 3-point bending selected, which will make everything that we do in this session so much easier. Additionally, if you use one of our templates, you also get the model database. The model database has already all the tests linked and everything, and will make your work so much easier. To pre-selected, we ship the VALIMAT with our test packages, which are just example template databases for different kinds of complexity of material cards. So yeah, as I already mentioned, you can basically pre-do your templates and save them as you want to with the workflow that you desire. The template database, as before mentioned, is already shipped with our software. And yeah, as I already mentioned, we have the tests up here. We have the generation of the material card down here. We can also use visualizations and validation models to validate the found parameters. And we can import the template databases. What's the advantages of the template database? As I already said, the test setups are pre-created, the parameters are already selected. There is little to no effort on your side to basically get the workflow going as intended. Quick things that we need to check before basically simulating is that the names and the geometry is basically correct. Really important is the gauge length, which will hand into the calculations quite a lot. Then we have the measurement curves. Be sure that they're not too long, too slow, or have any artificials in them. What's also important, but what we will come to later, is checking the starting values and the limits of design variables, since that might get like an issue later on for like really special materials. And what's also really important, if you go in here, for example, be sure that the correct load cases are linked. We can select the curves in the template database and see if they're correctly linked and if the measurements are filled in there. I'll hand over to my colleague again, who will introduce you to the MAT24.
So going further, so basically this is the main focus for today. So introduction into the MAT24 material model in LS-DYNA, and also going through setting up the Autofit process and also doing an Autofit workflow live based upon 3-point bending tests. Okay, so going further, so these are the test data that we have for 3-point bending for exemplarily shown for 4 different velocities. The dynamic tests are conducted with our own impetus system for 1 meter per second and for 4 meters per second. And the universal static testing is done on a universal testing machine for the static cases. So what is a MAT24 material model to our users who are new to LS-DYNA? So MAT24 is called in the LS-DYNA circles as the workhorse material model. It is the most commonly used elastic viscoplastic material model based on a vonMises yield surface. So naturally, because it's based on a vonMises yield surface, compression tension asymmetry is not supported. We do not have the option of defining any sort of viscoelasticity. And the most important thing that the plastic Poisson's ratio is constant, which means that plastic deformation takes place at a constant volume. Going further on MAT24, so MAT24 in LS-DYNA is a matte piecewise linear plasticity, as the name suggests. It's an elastic viscoplastic material model, and as I've mentioned before, based on the vonMises yield surface with an associated flow rule. The where MAT24 becomes really flexible is that the hardening curves can be defined arbitrarily for selected strain rates. And interpolation between the hardening curves for the different strain rates can either be performed linearly or by a logarithmic interpolation. If you want to find out more information on MAT24, please contact us directly, or you can also check online on the LS-DYNA manual. So the material that we're going to take a look at today is a polypropylene PPAEG 107 HP. So we already have a material card available for it, where we basically see the strain rate dependency and also the point that I mentioned about plastic Poisson's ratio being a constant. Okay, so now we have our test data, as I've shown before, conducted at different velocities. And basically now we would want to get from here to a material card. Okay, so as I mentioned before, we want to get from the test data to a material card. And how we're going to do this is by using our 3-point bending data as our basis for our optimization, as it's shown here with the pyramid. So we use the 3-point bending test data to get to our material card. So before we begin with the Autofit process, the first definition is to define our optimization strategy. How do we plan on getting to the material card? So basically here we follow a stepwise approach. So first we determine the elastic modulus, then the hardening curve, then the strain rate dependency, then we validate it based on all the given test data. So the optimization strategy that we have chosen for this example today is that we fit the Young's modulus on the dynamic low velocity, the hardening curve also on the dynamic low velocity, the strain rate dependency on the available different strain rates, and then we validate on all the different test velocities. We will do this live in the software too. So this is just as an introduction. Okay, so basically a first view of our Autofit window. So this is the Autofit graphical user interface where you have all the different steps here defined, and the optimization is carried out using a successive response surface method where we get to our optimized result in a stepwise iterative manner. Okay, so I think now we are ready to start operating on the software. So the first step in this autoflow work process is to get our auto values. So what are auto values? I'm sure a lot of you have heard this word auto values since day one. So what auto values are, what this auto values module does is basically get out reasonable start values for the material model based on all the tests that have been conducted. And whatever tests you define in your load cases. Yeah, so we have basically here defined all the 3-point bending tests along with the tensile test as our in the Autofit module or in the auto values module from where we get our start values from. Yeah, so data set validation optimization. So this is the first step, auto values. It is a pre-included function in VALIMAT, which will basically do this for you. As soon as we have defined our auto values function, the next step is that we carry out a first validation 3-point bend on the 3-point bending tests, which we have named here as validation 3-point bending auto. So what this basically does is use these estimated start values to give a first estimation of the material model, how the material model looks like with these start parameters. And then the modeler needs to make a decision that if it looks good or not, and then we go further into the optimization. Then, as I mentioned, in our stepwise approach, the next stage is the if the modeler decides that, no, I would like to have a better estimation of the parameters in my material model, you go further. And as you can see here in the model, under model settings in our model database, we have the validation / optimization window where all these different stages are predefined in the software. So first, because it's an elastic viscoplastic material model, we first go to define what is the Young's modulus. So we optimize the Young's modulus based on dynamic low velocity. What is really cool to see here is as soon as you select optimization Young's modulus, VALIMAT pre-select some options for you. For example, in the material card, you have the matte elastic, which basically reduces our computational time because we really do not go into a plastic regime for the optimization or determination of our Young's modulus. So this is one of the user-friendly features that VALIMAT has. Basically, it selects a elastic material model for you with no definitions for hardening or strain rate dependency or anything. And then we go down to the load cases. And then we have the definition for our dynamic low velocity. With the averaging here, it's also important. This also reduces our computational time. Basically, the scaling factor, as you see here, is set up to 0.3 of the, so 0.3 times the maximum force, which is in the elastic range for most thermoplastics that we have experience with. But this can be changed by the user according to his needs. Okay. Okay, so we have the design variables where we have the Young's modulus that comes directly from the auto values, and then an estimation for the Poisson's ratio. Yeah, then we move on to our next step in the optimization process, which is getting information on hardening or the flow data. So if you go to the top again to model settings, as I mentioned before, you have to select optimization hardening or Young's modulus. Optimization hardening. As soon as you select optimization hardening, again, VALIMAT pre-selects all these options for you. If you go into idealization, we have the unit system, we have the type of solver, the input tech implemented means that the model is already, VALIMAT is already capable of modeling this or generating a mesh for this automatically. In cases where we do not have a readily implemented finite element model, we go into customized input deck here. Again, more information on this would be in the talk from Mr. Hirschman next week. So we have idealization type, that is important, shell. As my colleague Mr. Schober mentioned before, we are going to generate a MAT24 card based on shells with an element size of 2 millimeters. Okay, then as we scroll down, we have our material card, which is, can you make it bigger? Yeah, which is the MAT piecewise linear plasticity, which is pre-selected by VALIMAT. Then as we go to the hardening function, because the main intention of this step in the optimization is the hardening function. So we have the hardening function that is defined as a 4A model, new 0.5. We have a lot more options. So we have polymer law, we have a bilinear model, a lot of different implementations to get out the hardening curve. And as you select a hardening curve, we have all the design variables initialized. One interesting aspect here also is the strain range up to option, which basically defines how big are your cards written out. So what is the strain range of your material card itself? If you go into design variables, Christoph. So here we have the Young's modulus, we have the Poisson's ratio, we have our yield, Y, we have our different design variables. Okay, so basically the hardening function is defined by this function. It's the same function. And I wanted to show this window because I think it's better that we know what each of these design variables mean. So as you see, HH, HY is basically your yield point. Then we have HET, which basically defines the slope, how high your function goes in the plastic regime. And then we come to the VP factor later on in our strain rate optimization, which basically defines the height of your interpolation of different strain rates. You must be wondering what P-run, auto, what do these values mean? I will get to that once I'm done setting up the workflow. Yeah. The next step is after hardening, we go into our definition of strain rate dependency. So basically optimizing the strain rate dependency. So here again, under validation / optimization, we select optimization strain rate. And again, as I've mentioned, some options are again pre-selected by into our strain rate dependency. Here it's defined as a table. Strain rate dependency curve is defined by a Johnson-Cook model, which is the most popular. I'm sure every one of you knows about the Johnson-Cook model. But along with Johnson-Cook, we have some other implementations also included in VALIMAT. So Cowper-Simon, Kang, and also a power law. And if we maximize it further, so the strain rate dependency is based on the plastic strain value instead of a total strain. Again, this is a user specific option. Then we basically have 8 strain rates here defined because that is the maximum number of strain rates we can define for a LS-DYNA card. And then once you go down to your load cases, here we have 3 different velocities because that's our main goal here is to optimize the material card for strain rate dependency. What is also interesting here is under averaging, VALIMAT pre-selects the averaging method to represent 0.7 or 70% of the maximum displacement in the test, because the rest areas in this stage of the optimization not so interesting for us. Again, it's a user, it's a feature, or this value is recommended by VALIMAT, but then it is again dependent on the material you test and also based on the user. So we have all the different design variables here again, and the important design variables in this case are VP and VEPS PKT, which basically means strain rate parameter and our initial strain rate. Okay, and then as soon as we're done with these steps, we would want to check how the optimized material card performance is, and then that's why we define a validation step at the end. Under validation, yeah, and then we can select symmetry of the model to be a larger one, maybe a full model or a half model, depending on the user preference. And then we are basically now ready to start our Autofit process. Okay, so starting the Autofit process is, I think you have noticed. Okay, so what is important is that we have all these steps defined with an increasing index. So we have 0, 0, 0, 1, 1, 0. So basically they must be defined with an increasing index, and then you select all these things that we have defined and right click on the software to start our Autofit. Okay, so we have all our design variables here that are shown along with our visualization module. So the design variables I've mentioned before, and I will clarify what prun and auto mean. So as you see here from auto values, the next step is the validation 3-point bending auto, which basically gets the values from the auto value step. So auto always means that these are the auto values that are generated, and prun means that we get the values from the previous run. So they are built up in a pyramid manner. So basically we determine parameters step by step, and then we validate them at the end. As you can also see here, we have a few more validations here defined for clamped bending, for tensile test, and for puncture test. So if we go back to the test database to just show all the test results that we have here. So we have all the different tests here. So 3-point bending we have discussed. Then we have the clamped bending or the tension bending. Then we have the tensile tests, and then the puncture test. Basically now we are, I think, ready to start our Autofit. I would want to welcome any questions now before we start the Autofit process from the audience. Hi everyone, I apologize for the short delay because we seem to be having some problems with the resolution of the images that some of our viewers are getting. So we checked some few things internally. I hope the stream works better now. So we left off with starting the Autofit function, and I was in the middle of telling you that we have defined further validations for clamped bending, for puncture, and for the tensile test. So basically, we want to validate our card for all the different load cases that we have tested. Okay, so how do you start the Autofit? You basically select all your models and then right click and say Autofit. Okay, and as it is shown here, all the validation steps get the design variables from their previous steps from which they were from which the design variables were optimized. We have different options here in the GUI, in the graphical user interface for Autofit. We have the run. We can even open the LS-opt viewer directly from the user interface to check with how the design variables are performing over different iterations. So how they are coming together and how they are varying. Okay, so we can start the optimization process. So at first, as soon as you click on the run button, VALIMAT communicates with Python, and then Python calls the LS-opt and the LS-DYNA to run the simulations. First, we get our auto values. That step is done. Then we check how the start parameters or what is the performance of the start parameters in comparison to the test data that is running now. As you can see, so there is a progress bar, you can say, for validation auto. We should have the results shortly. A first estimation of how the material model looks like. We have our first result for the validation 3-point bending for the auto values. As you can see here, it is already quite a good estimation of the test data. What could be better defined is the hardening curve for the low dynamic velocity that is in blue. That is our basis for our optimization in the next steps. But in principle, as you can see from a first look, the material model, so it's headed in the right direction from the start parameters. And you can also, if you can see the screen, you can also read out the start parameters here, which is Young's modulus of around 2,400 megapascal. Okay, it'll take a little time. Yeah, so we have the first optimization result for the Young's modulus. As you can see the dynamic nature of the test results. We have some small oscillations in them. And also it can be bettered, but as this is a training example, we have just run it for a lesser number of iterations. So to get a quick result, but it's already a good estimation. So here we can see the optimization result, and in comparison to the test curves, we can compare it to the force displacement curves that we get from the tests. If we zoom in to the beginning area there, so we see that it's already a good representation of the Young's modulus of the material for the different load curves. Okay, so the Autofit process is running. It will take a little time, and I think in the meanwhile we could go ahead a little with the presentation. So I'll give you a small overview on our simple failure approach. Okay, so we can start a small discussion on our simple failure. So for a material model, so we have two important aspects. So one is the deformation behavior, and then the second aspect is the failure behavior. So typically we have stress-based and then strain-based failure criteria. So stress-based is typically used in the composites area, and then for thermoplastics, we generally use our strain-based criteria. So if we go further, so the strain-based criteria. So we have varying levels of complexity with the strain-based criteria. So the first one that comes to mind is the equivalent plastic strain that is already included in the MAT24 material model. And some more complex material models have damage models included in their formulation already, like the other well-known complex material model from LS-DYNA, the MAT-SAMP1 or the MAT-187. We will have a detailed discussion on how to fit this material model next week. Okay, then basically the additional failure models in LS-DYNA with the keyword mat add erosion. We have in these we have the options between DIEM and Gizmo. DIEM is your classical damage initiation and evolution model. Gizmo is a more specialized approach in failure. Okay, so our typical damage model looks like that. So we have stress over equivalent plastic strain. And basically the red curve here shows the undamaged stress. And then the orange curve here shows a linear damage. So what this picture basically shows here is in the stress, we have a value of the critical strain. And as soon as we reach the critical strain, as shown in the picture on the right, your damage variable starts to evolve. And then there are different ways how you can define your damage evolution. You can do it linearly, as shown with the orange curve, or you can do it exponentially, as it's with the black one. I have mentioned something about DIEM and Gizmo. So DIEM for most material modelers out there is a familiar model. So it's a damage initiation evolution model. So your damage initiates at a certain critical strain, and then it evolves until it reaches a value of say 1, because the damage variable is always between 0 and 1. And as soon as it reaches 1, we have failure. Okay. So what is the big difference between Gizmo and DIEM? This would be dealt with more in detail in the talk from Mr. Hirschman next week, but I would just like to give a small introduction. So the big difference between them is that when we consider ductile damage behavior of plastics, Gizmo offers us an opportunity to basically go in depth over to consider element regularization. And in plastics, we will see next week how important that is. Or DIEM, the advantage with a DIEM model, first of all, is the familiarity of such a model, and also that it's more flexible with your strain rate scaling. Yeah, as I said here, Gizmo has a fixed scale for strain rate scaling, and DIEM has a more flexible scale for strain rate scaling. And as I said, more on the talk from Mr. Hirschman next week. So it is possible that we have different strain rate scaling for a different reaxiality. If we go very much in depth with modeling failure, then the correct way or the more accurate way to approach it would be to have the exact values of strain rate scaling also dependent on the triaxiality levels. Okay, so this picture also was shown by Mr. Reithofer on the first day. So what does this picture show you? So basically, we have all our different load cases that are tested classically. So you have your compression with a triaxiality of minus 0.33, and you have your shear with a triaxiality of 0. Then you have your uniaxial tension with 0.33, and then we have a notched tension sample here with a triaxiality that lies in between 0.33 and 0.66, and the classical puncture test with the triaxiality of 0.66. So what are the practical difficulties that one experiences when we would want to determine such approaches for plastics. So the first thing is that in compression, compression failure is mostly buckling, or we typically have no failure at all. The problem with shear tests, especially for plastics, is we might, for very ductile materials, see that the failure is not really happening exactly in the shear zones, but it's happening in other places. And also for ductile thermoplastics, it's a challenging test method to perform to get pure shear behavior out. So these icons at the top, they are basically the tests that are conducted with impetus, and we are in the range between 0.33 and 0.66. So we do all our different tests. So we have our 3-point bending, which is with a triaxiality factor of 0.33. We have our puncture test with a triaxiality factor of 0.66. And then we have the tension bending, which lies in between. Then we have our classical tensile test. So, as I told you, that the topic of this session today was simple failure. We want to model this using a very simple approach. So I would say I choose DIEM, which is the damage initiation evolution model, and basically assume that I have no failure under compression. And my uniaxial tension and shear behaviors are the same. And in a typical approach, as you can see with the dotted line here, you would have to adjust the biaxial behavior depending on your test result. But as I said, this is a simple failure approach. And one more assumption from our side is that we use an average of all the different measurements, the failure strain from all the different measurements, and then we keep the tensile side completely constant with this failure strain. How good are the results if we have such a approximation? That I would show you in the software live, but going further. Okay, so going further with the software itself, VALIMAT, how do we set up failure? Okay, so this window everyone is familiar with by now, I hope. We have defined in all our previous steps, we have defined hardening, we have defined strain rate behavior. Now we come to defining damage. So we have damage failure, and one thing to consider is we will set up the failure, but we are not going to optimize it. So it's just a setup of failure. So we have the damage failure models. We have add erosion DIEM. As I said, we would be dealing with add erosion DIEM once you click on that. Then under fracture, we have more options that open up for ductile damage settings. And in ductile damage settings, we have a lot of these different functions incorporated again. So as you can see here, the simplest one is plastic equivalent strain. We have the Fourier piecewise linear, which is a simplified form of the piecewise linear interpolation. So for this training exercise, I'm using the piecewise linear interpolation with some values of the lower triax and upper triax. And as soon as you select these under design variables, we have the option to define all these parameters. Okay, so as you see here, I have defined some failure strains, plastic failure strains. How do I get to these values? So if you remember, once we go out into a model database, so this is this one. Can we go to the other series that is run through? Yeah. So this is basically we have run through the complete series. So all the tests that we have demonstrated with the Autofit workflow. There is one that we have run earlier. So we see the puncture test without failure now for first. So this is something we already set up and we have a result for that. This is the puncture test with no failure included, as it was done in the Autofit workflow. And there is one thing that is clearly evident from this model here is that at the beginning stage, the material model represents the test curve quite well, because that is the bending dominated area and our material card is validated or is derived from bending. But in a higher strain regime, we go far away from the actual curve. That is because we do not have any sort of tension compression asymmetry in the model, which is required to actually model this more accurately. Okay, so if we go into the other window, so one of the options that VALIMAT also gives you is to get out your failure strains. So how does VALIMAT do that? So we have this option called failure evaluation under XY plot. So what this does, so if we go to our test curves, so if we go into a test curve for puncture test, these are the raw data for all the different tests that have been conducted in puncture. So we go into one evaluation for the puncture test. Okay, under evaluation here, under identification of failure. So we have this setting of T end and T fail. What is T end and what is T fail? So T end is the end time of the test and T fail is the time where failure occurs. How do we get these values? So using engineering judgment by looking at the force displacement curves. So if we look at the force displacement curve now for the individual tests of the measurement signal. All right, so as you can see here, so if we could move around the curves here to get average of the failure, and then we can using engineering judgment, we can say this time is where we have failure in our test, and this is the time where the test is ending. And we could do this manually in VALIMAT. Yeah, and then once you have those things, and then you click on T end. Yeah, and then as you adjust the curve on the right, if you say get, and then you get the time in here. And this is how you set up T end and T fail once you're doing the test. And this really helps us in the modeling part that comes next. So failure evaluation on case name, we have the option of failure evaluation. Okay, what this button does, if you go into next window and the stress strain curve. All right, so basically it gives you the failure points from the test. And these are very good indicators for us to start with our failure modeling. So if we just adjust the curve here, we could probably look at some averaged value. So around 40%, 42%. So, and then we repeat the same for all the different load cases that we have. And then what we do is an average of all these different failure strains. And that is what is in the, so if you go into the failure model that I've set up here. So an average of all these strains is basically given on the table here. And then the first two values are basically our compression side. We set it to a really high value so that we don't have failure. And then we have this averaged plastic strain value. If you go a bit more down, we have failure strain rate. This is simple failure, and we have mostly dynamic load cases. So as an assumption, I have not considered the effect of failure strain rate here. So we do not have strain rate dependency for failure in this example. Then post-failure, which is very interesting, but again, in as an assumption for a simple case, I have assumed that it's 0.01. So we saw the optimization Young's modulus. Then the flow data has been optimized. The hardening curve, see here, it represents our test curve very well. Then we have optimization strain rate. Again, you see here the strain rate is depicted again really well by the model. We can take a look at the results in the model that I have run earlier. So as you see here, this is the validation 3-point bending. I have included a couple more strain rates compared to the 3 that we have in the training example that I've shown you. You can see here the material model captures the test data very well under under bending. Then we have all the different load cases. So we have the clamp bending, which is again, and then the tension test, because the model is calibrated on a bend on a 3-point bending test, and we do not have tension compression asymmetry in the model. The tension test is not captured 100%. Then we have our puncture test. And then we see what is the influence when we have failure. So if we go into the puncture test with the failure setting that I have used. So see, we have failure. The force peak matches quite well. The behavior is stiffer compared to the test data because of the tension lack of tension. This is basically the Autofit workflow that I have gone through here. What we will do next is get out all the results into a report, which is also supported by VALIMAT using a function we have called auto-report, and then write out the material card for this material. So I will hand over now to my colleague, Mr. Schober, who will show you how this is done.
Thank you very much, Mr. Potoguchi. So I will show you now how to basically create a report in VALIMAT, which is very, very easy and very convenient. We'll basically just select all the last models. In this case, I'm using all the failure models because why not? We go into post-processing and go into create report. Now this window pops up. In this window, we already have like the different cases selected as per indice. We'll use the first indice and say choose a file. From here on, we'll select a template. There is a template that is already sent with VALIMAT. In this case, I've prepared something quite short, and in here, we will basically go to the 3 dots and tell it where to save the final report. We'll go to desktop and we'll just call it report mat24 and go to save. In this case, I'll overwrite the last report and then we click on OK. Through the selected indices, we can clearly get like the models matching to any position that you would actually want. For now, that is how our usual report looks like. We called it sample report with our material and the temperature. We have our disclaimer. We have our outline telling it which package it is and what the reverse engineering is based on. We have a short overview slide. All these can be filled in automatically via our DB template database output. We have like one more slide on how the reverse engineering works. And then we have each load case. First, the measurement results, the raw data that is put into the report. And on the other hand, we have the validation results of the simulations. In this case, we could also write out with the failure points, but we did not choose to. We can also get these figures into the appendix of the report by simply redoing everything with the indices and align them correctly. We can choose to have either stress strain or force displacement output. In this case, you can see we chose to implement the failure points as well. We can also have the clamped bending in this case and the puncture. Here we can see the failure points are a little late, but that's, as we discussed, because of the averaged strain, failure strain. To show you a little bit how the report works in the background, I can just tell you that it's extremely customizable. We have like a whole file on how to get your customization going, whichever way you wanted to. And for like further information and for further help, we were glad to help you at valimat.support.48.at. So the actual material card is written out by just simply using one of the validation models. We'll just use the create part button on the left lower side. Here we can basically select a template file that is only relevant for the header. We have a pre-made sample header, which basically also already puts in all the information that we need. We have the material, we have the temperature, we have the humidity, we have the series and everything we would want. There's also background information shared, such as like the idealization, the element used, the element size used, the integration points through thickness, strains, strain rates, and yeah, you can also customize it to basically pretty much every single load case. Now, if we click on OK, we can tell it where it should be saved. So we'll tell it it's our material, and then just write an input file from it. We'll save it. And then we can go to the desktop and see what the thing wrote out. So that is a typical material card with our pre-made header. It shows pretty much every information that we need. And in the background, we have the load curves for LS-DYNA for each different strain rate. And we can go ahead and implement that material input into any simulation that we want. So that is it from my part, I think. And I'll hand over to Mr. Potaguchi again.
Okay, so I think we have come to the end of our presentation. I would just want to remind you that tomorrow we have the session on lessons learned, so a summary of the whole week, outlook, and some upcoming features in the new VALIMAT version. So thank you, everyone, and I would open the floor now for questions. Thank you.